All right, so I'm calling this section 7.7 natural logs. We talked a little bit on Friday. Like I said, I probably didn't do it quite justice, but we kind of talked about how what E really is, how it kind of comes about. But basically, we're going to look at just kind of defining E, see how it works with what we've learned about logarithms today. Depending on how this goes, tomorrow we'll start looking at application questions. Like we're going to see that this E is really important if you're talking about compound interest. So it's used in finance quite a bit. But E in these notes, E is going to be an irrational number. Kind of like pi. Good morning. Oops, I just go to the bottom. But it's going to be an irrational number like pi. Remember, an irrational number is like a decimal that like goes on forever and it doesn't repeat. It's an irrational number. And if you put this on most calculators, like I said, I don't know how many of you guys have graphing calculators, but a lot of calculators, you will see there is an E button. You might, like on the graphing calculator, you're going to do second, then the ln. So if you put like E up to the first in your calculator, or just kind of remember, it's approximately 2.7182, and it, like I said, it goes on forever, but it's approximately, usually if I don't have a calculator and I'm doing it like a calculator that has an E button, I will just put in like 2.71, I'll kind of approximate, or 2.72. Like I said, E often occurs as the base of exponential and logarithmic functions that describe real world scenarios. Really the most common one I can think of is compound interest, which is basically if your interest is being calculated like all the time in a bank account, which oftentimes is the case. That like I said, in finance, it does come up quite a bit. We're going to look at exponential functions with base E, and we call these natural base exponential functions. So for example, if we have a function like this, like E up to the X, we say that has a natural base. So E is considered natural because it usually represents kind of like a natural growth. Like I said, if you weren't here on Friday, or if you didn't understand, I did post an article that kind of explains that. But basically the idea is that if you have something that's growing, the thing that grows is growing as well when it comes to finance. So it's kind of like more of a natural growth versus if you just assume something just doubles out of nowhere. But you got to think it's growing all the time. So this is kind of a better way to model a lot of things that grow into the real world versus other bases. What we're mostly interested in today is base E logarithmic functions. We call these natural logarithms. I'm just going to put logs for instead of logarithm, but we call these natural logs. So for example, if you had a function that looks like, oops, I'm sorry, I know my handwriting is not the greatest, and I'll zoom out. I just need to zoom in so I can write this. But if you have a log with a base of E, we call this a natural logarithm. But you're never going to see it really written like this, like log base E. Instead of writing, ooh, I'll get rid of this. Okay, sorry. But you're always going to see this abbreviated, here, I'll write it in function notation, but you're going to see this ln of x. So if you ever see, it's called natural log, this ln, that's like how you read it, like from reading that, that's the natural log of x. But, and if you look on your calculator, if you have a graphing calculator, you're going to see there is a button, it's right on the graphing calculator, it's right below the log button, but you're going to see there's an ln button. So if you're ever doing a natural log, make sure you use that button there. But basically, anytime you have a log with a base of E, we use the ln notation. So these are the same as each other, but like I said, you're never going to really see it like here on the left. You're always just going to write the ln. So, and one thing to keep in mind, a natural log is no different than the logs we've done before. It just means you have a log with a base of E. So it's kind of like a special type of log because, like I said, a lot of different applications are going to use E as like the base of the exponential form. So one thing just to kind of keep in mind, everything we've learned about logarithms applies to these natural logarithms. That's basically kind of what we're going to do in the rest of these notes. We're just going to kind of go back through a lot of the things we've seen. So this is actually a pretty good review of a lot of the topics we've seen so far in chapter 7. So you can still convert between forms. If you kind of remember the general form, you have your log of your base. It's going to equal your power. And then this is kind of like your input, I guess you could call it. I don't know exactly what to call that inside part, but basically since E is our base, we're going to have a natural log of 24. Like basically what it equals is what you input into your function and then equals your power. And they're just asking us to write it in logarithmic form, but if we were solving this, I mean, you would just put in your calculator the natural log of 24, which if you did that, you'd see it's about 3.18. But they're not asking us to solve, they're just asking us to put it in this form. Similar idea here, since it's E is our base, we're going to have a natural log. What it equals, this is kind of like your input. And then you're going to set it equal to the power, which would be 9. And similar idea here, if you were writing this in logarithmic form, you'd have a natural log. 72 is going to be that input, and then it's going to equal your power. And if we'll see eventually when we're looking at some solving, but basically to solve these, you just kind of type that natural log of 72 and subtract 5 from it, you would get your solution, for example, if we were solving. But right now, they're just asking you to put it in this log form. Similar idea, you can rewrite these in exponential form. So basically, your base, remember, is E. So you would have E, remember, this is your power. So you'd have E up to the 58th equals your input, which is X. So same idea here. This would be E up to the X equals 6. E up to the 32nd equals X minus 9. So if you remember, I know it's probably been a little bit, but same idea. We changed between forms when we were just looking at any other kind of log. But just remember, if you see the natural log, your base is going to be E. And let me know too, especially I know I'm going a little bit quick potentially, but if you do have any questions, just feel free to stop me. But this is just converting between forms. We're going to see that our properties we've learned also apply. So if you remember kind of what we looked at with logarithm properties. So remember, if you add two logarithms, you can multiply the inputs. So like you could multiply the 3 times the 16. So this would really be ln of 48. And they're just asking you to write it as a single logarithm. Obviously, you could put that in your calculator if you wanted to figure out what that equals. But like I said, when you put it in your calculator, make sure you use the natural log button. Pretty much every scientific calculator should have this. But if your calculator doesn't, let me know. I mean, you could also download like one of those apps that we've been using. Those should also have it. Like, let me just see really quick. Like if you're using this Calculate 84, for example, like you would see that the natural log button's right here on the like bottom, the left bottomish side, right below the log button. Similar idea here. Remember, if you have a number in front of your logarithm, you can use the power rule. Like, so that would really be, oops, like hitting the bottom of my iPad, my bad. But that would really be 3 squared. You'd really have ln of 63 minus ln of 9. Like you raise that 2 up to a power. And then remember, when you subtract natural logs, you just divide. So 63 divided by 9, that would be 7. So like I said, nothing really new from what we've seen. 9, this one, like I said, you'd want to deal with the coefficients first, bring those back up as powers. So this would be ln. Remember, you could just type in your calculator 64 up to the 1/3, or really that's the cube root of 64. If you know that in your head, that would be like, or if you can see that, that would just be 4. Or like I said, you could type that in 64 up to, just make sure you put parentheses, 1 divided by 3. You should see you get 4 in your calculator. And then this isn't going to, I mean, we got a variable, so it would just be x squared. So if we condense these, we would just have ln of 4x squared. There's nothing, I mean, obviously with that variable, there's not much we can do with it right now, at least. Similar idea, we can expand logarithms in the same way. Since you have 5 times x, oops, you could just separate that as ln 5 plus ln of x. If you see a question like 11, there's 2 ways you could do it. My advice is honestly, it might be just best to deal with the power first. Like this would really be ln of a to the 6 over b squared. And then you could just separate this out. Like this would be ln of a to the 6 minus ln b squared. And then actually you should also bring the powers in front. So I guess the final answer would be 6. Yeah, let me zoom in. So this is getting pretty bad. Sorry, that's kind of sloppy. That's an a up to the 6th power. So if you bring that 6 in front, you'd have 6 ln of a minus 2 ln of b. Similar idea here. I mean, like I said, and this should be reviewed. Like I said, I mean, it's nothing new. We're just looking at it. Instead of writing log, you have ln. Like, I mean, that's like, I mean, so all these properties aren't really new. Just remember, if you have a radical, there's 2 ways you could actually do this question. One is you could just take a 1/3 in front, or you could also rewrite this. Like, remember, you take, like, if you wrote it in an exponential form, it's your power divided by your root. So like this would really be m up to the 2/3. This would really be n up to the 1/3. Like you could kind of get rid of that root by writing it like this. Then simply just separate these. Since it's multiplication, you would put a plus sign between your 2 logs. Oops. Oh yeah, there would be an n there. Yeah, n's kind of a bad variable, I feel like, to use when you're using natural logs, but and then you would bring your powers in front. And like I said, if you're doing these on your own, feel free to, like, I'm writing each step individually, but if you want to do multiple steps at the same time, like if you could go straight like from here to here, that's totally fine. Like eventually when we have our quiz over these, feel free to, like, if you can do some steps in your head, I don't need to see each individual step. Like I expect some of you guys to be able to do like, oh, I'm gonna separate it with an addition sign, but then I got to move the power in front. Like I totally would expect some of you guys can kind of see, or you can kind of do parts of it in your head without writing it out. So feel free to, I know like on these notes, I'm pretty much writing most steps out individually, but if you can do it with less steps, feel free when we're on our, eventually when we have our chapter 7 quiz, which might be later this week. We'll kind of see how it goes. We got one more thing to look at. Tomorrow we're going to look at compound interest problems. So maybe I'll post like a review Wednesday, maybe post the quiz, give you maybe Thursday, Friday to kind of look at it or something like that. But we're pretty much done with chapter 7. I'll double check that there's not anything else that I'm missing, but so just kind of reiterate. So we saw like all the properties we've seen with logs apply. You can change between forms the same way. You can condense, you can expand using those same properties. So a lot of textbooks really, like, they always kind of do these natural logs separately, but there's really nothing different except, like I said, it's this base E. And the reason I waited to do this is because we hadn't talked about what E was, like how it's this irrational number. But like I said, E, where it comes from, it's basically a way to show kind of it's a better way to model natural growth if you have something that's growing and what already growed starts growing. So a lot of times it relates to interest, because if you're investing money, your interest is also going to start gaining interest, and that interest is going to start gaining interest. So um, it's a little bit more of a natural thing than just like two, or like a base of two or a base of three. Like this kind of models natural growth. Um, we're going to see that solving equations, really the properties themselves are the same. If you have the same log on both sides, you can just cancel it out. The reason for this, I feel like maybe I didn't do the greatest job. The reason you can get rid of your logs is because if you take the base, which in this case would be e, and you raise both sides up to the e, basically it just cancels out the logs on both parts. But basically, if you see the same log on both sides, you can just get rid of it. So I mean, you would just have 4x minus 27 equals 15 minus 2x. Just solve this equation. I'm going to add the x's to the other side, so I get 6x. I'm going to add the 27 to this side. So I'm just going to kind of do that all at once. So basically, I get 6x equals 42. Divide by 6, you would get 7. You do want to be careful because you can still get extraneous solutions. So remember, you want to just plug this back in. It doesn't even like it's for sure. I mean, as long as you just didn't do anything mathematically wrong, it's going to be the same, but you just want to make sure if you plug it back in, do you get 0 or a negative number? If you ever get 0 or a negative number inside of a logarithm, that's a problem. Like you can't have ln of 0 and you can't have ln of a negative number. If you're ever plugging back your solution and you get either one of those cases, it's extraneous. So it's not even more the check if they're the same. I mean, obviously they should be the same when you plug it in, like on both sides of your equation. But that as long as you didn't do anything like crazy wrong with your math, that's never really going to be an issue. It's more so, are you going to ever get a negative when you plug it back in, or 0? But if I plug 7 into that right natural log, I would get 15. Oops, sorry about this. I would get 15 minus 2 times 7. Well, that would be 1, so that's good. 4 times 7 minus 27, that would be 28 minus 27. That's also 1. So good, no negatives, no 0. We're good. 14's kind of a, here, I'm gonna just use a different color maybe. 14's a pretty similar idea. The only thing is, before you cancel out your logs, just remember this coefficient in front, you can raise that, that's really a power. Like, so this would really be k squared. So you want to make sure, like, if you do have a coefficient, because you don't want to divide the 2 to the other side, like that's not really going to do you any good. So you want to make sure if you have a log on both sides, if it's possible to condense it so like everything's in the input part. That's kind of a key thing. Oops, I didn't mean to erase. But once you've done that, you could just get rid of your logs. You'd have k squared equals 2k plus 15. Anytime you have a quadratic, you kind of want to get everything to the same side. So I'm going to subtract the 2k and the 15. If I subtract those over, sorry, it's kind of hard for me to like fit that, but basically if I subtract everything to the left side, and then you just want to see, does this factor? If it does, awesome. At worst case, you might have to do quadratic formula, but this looks like it should be good. What would it be? It'd be minus 5 plus 3. Like, what multiplies to negative 15 adds up to negative 2. So you would get 5. You would get negative 3. And like I said, we want to just double check. If I plug these back into my original equation, am I ever going to have a negative input? I mean, 5 is not going to cause any issues. I mean, that would be 5. This would be 25. So I mean, that's all good. But negative 3 is a problem, because if I plug negative 3 in for k, that's going to give me a negative input into a log or a natural log, which is a problem. So that's extraneous. Even though if you plug it into this right side, I mean, that would be negative 6 plus 15, which would be positive, which like if you're plugging it into any of the log parts in the original equation and you get either 0 or a negative input, that's a problem. So that's really what you're looking for when you're checking for extraneous solution. It doesn't even, like, I mean, if you plug these in your calculators, you should see that they're the same, but more so you're on the lookout to see if you get a negative input in a log. or zero. Zero is also, you can't have a natural log of zero. And if you don't like, I mean, I know this isn't like a great thing, but if you plug like in your calculator, if you did ln of zero, for example, it's going to give you a domain error. If you did ln of -2, it's also going to give you a non-real answer. If you plug that like in a graphing calculator, here, I'll just show you that. But and this isn't like a very great explanation, but you, like I said, if you plug in ln of zero, it's going to say not a number, ln of -2. Oops. But if you do ln of like a negative number, for example, it's this wouldn't happen in a graphing calculator, but it gives you like an imaginary solution if you see, which is kind of like a strange thing, but it's a non-real solution. So we're not worried about finding imaginary solutions. So if you are using this app, if you actually have a real graphing calculator, it will say like not a real solution. The reason why, I don't know, I wasn't going to really graph too many of these, but if you graph like, for example, just log of x, you're going to see your graph kind of looks like this. It's kind of deceiving, actually. It should, I don't want to like stop sharing my screen because God forbid it's not going to work. Let me see, can I just make sure, hopefully not. Okay. If you go to desmos.com, let's just see. I don't want to get off this. Let me see if this looks any better. Oh, how do you do a log? So I got log of x. Yeah, because on the graphing calculator, you should see basically your graph. It looks a little bit deceiving. Let me see if I can zoom in. If you kind of remember when we talked about asymptotes, it's basically going to get really, really close to the line y equals 0. Or wait, sorry, x equals 0. Like, but it's going to get really, really, really close. But you're going to see it's never going to cross. So your function's never going to have an x value of 0, and it's never going to have any negative values. So it's just based on the function why this happens. And I know I just graphed log of x. This would pretty much be true for any like variation that we would see at least. Okay, so we'll just look at a few more of these. How are we doing on time? Okay, we're doing all right. Similar idea. So far, these first two we saw, if you had like a log on both sides, these are actually all pretty much the same. I mean, 15 would be pretty much the same idea. You'd want to condense your logarithms though. So if you combine, remember, if you have minus, you can divide. So 72 divided by 4, that would be 18. And then on this side, we're adding, so we would multiply, and I'm just going to distribute that 6. So it would be 6a minus 12. Get rid of our logarithms. You would add the 12, that would be 30. Divide by 6, you would get 5. And then if you plug this, like just double check, if I plug this in, I mean, this is the only spot with the variable. I mean, that would be +4, so no issues there. Or sorry, that would be +3. Sorry, it's 5, not 6. But either way, it doesn't matter. I mean, it would be positive. Sorry, I said the wrong thing there, but you would see if you plug it back into the original, you're not going to have any inputs that are negative. You can get it. One thing just to be clear, you can plug it in and get a negative answer. It's just like when you're looking at your inputs, are you ever going to have natural log of either 0 or negative? It's not about like your actual result or your answer, but just when you input it in, are you going to have any issues? I'm going to skip 16. There's nothing really, I mean, you would have to raise this as a power and you'd want to FOIL it out. Like it would, maybe I'll just kind of like, but it would really be the whole thing squared. So you'd want to FOIL this out. Don't just raise each piece. So you'd really get m squared, like m squared plus 8m, sorry, plus 16. Like you FOIL that out. And then you would just can't, I guess here, I'll just finish this one. We're pretty committed. So you would get rid of your logs. You'd want to subtract that 4 over. And then you just want to factor this. This one does factor out. Sorry, I'm running out of space, but it'd be m plus 6, m plus 2. So if you solve those, you would just get -6 and -2. And then if you just check, if you plug these back into your original equation, like I said, you're just looking at the input part. So n plus 4, if I plug in -2, that's okay, because I would get +2. But if I plug in -6, that's a problem, because -6 plus 4, that would be -2. So that's not a solution. I don't even care what this like equals. Like, I mean, it's just you can't have a nat, because if you did work it out, you would have -6 plus 4, that would be -2. If you square that, you would get a positive value, but it's the fact that you can't have an input that is negative. Let me skip, because there's a lot of problems. Let me just kind of look at some different types. If you saw one like this, basically, you kind of want to change it to exponential form, or really there's kind of two trains of thought with this. Basically, to get rid of a natural log, you take e up to both sides. Or basically, you would just be writing it in exponential form, because what happens is that would cancel, and you would have e squared. So then you would just divide by 8, and then really you're just going to put this in your calculator. So in a graphing calculator, most calculators, you're going to press second, and then wherever your natural log button, you should see that above it in yellow, or the different color, it's e of x. So you would just do e up to the second power, close your parentheses, then divide by 8, but it's approximately 0.92. It goes on. I mean, I think 2 decimal places is fine. But if you want to put more, if you're trying to be super accurate, it's your world. So that's kind of the idea. If you have a single log equals a number, like for example, this one, you'd want to first condense your logarithms. But basically, like I said, you can basically think of it 2 ways. To get rid of a log, like one natural log, you take e up to both sides. Or you could just do like on the front when we changed forms, basically it would be e up to the 7th power equals this x over 9, and then just solve this equation. So you would just multiply 9 to both sides. So then in your calculator, you would just do 9 times e up to the 7th. If you do that, it's kind of big, but it's 9,869 .70, I guess, if you round the 2 places. But like I said, I mean, similar idea. If you see like a problem like this, basically to get rid of your e, you take the natural log of both sides. Because what happens is that cancels out your e, and you just get your exponent, which in this problem would just be x. And then you're just going to put this ln of 57 in your calculator. So the natural log ln 57 press equals, it's approximately 4.04. And just to maybe show you, sorry, I've been just kind of using my graphing calculator here, but like I said, I'll like plug that in. Oops, I could quit. You would just do, like I said, ln of 57, so on and so on. To like do those power ones, like I think what we just have before. We did 9 times e to the 7th, 9 times second ln up to the 7th. That's how I got that previous answer. Just to kind of see how I'm plugging these in. So let me just see, is there any type of problem we really haven't done? Okay, we'll do at least one more of these. Let's look at a more complicated one. Let's just do 22. So if you had a question like 22, before you take the natural log of both sides, you want to get the exponential part by itself, like the e part by itself. So you would subtract the 3. This would be 84. You want to divide that 2. So you'd have e c minus 9 equals half of 84 would be 42. And then to get rid of your like this base of e, you take the natural log of both sides, because that cancels out your e. So you just bring down that exponent. So c minus 9. And then on the right side, you still have the natural log of 42. So you're just going to add the 9 over. And then in your calculator, you're just going to do the natural log of 42 plus 9. So the natural log of 42. Just make sure you close that parentheses. That's one thing, like if you don't close the parentheses, it's going to think that the 9's being added to the 42 on the inside of your log, which is not what you want. But it's approximately 12.74 if you round to 2 places. But feel free to, like, I mean, especially like on something like this, feel free to round however you'd like. If this was like your quiz. If it's something like on Delta Math, make sure you're reading the directions because they might tell you to round to a certain amount of digits. But there's no directions here what it says to round to, so do whatever you'd like. I would at least put at least one decimal place. That you don't want to usually round to like whole numbers usually because that could cause some error, too much error if you're actually doing something more with these. But that's it for these. We've got about 10 minutes, so I will leave it to you. I mean, I could post the Delta Math assignment if you want to practice some of these concepts, but like I said, there really isn't anything new here other than you're dealing with E. Or if you see an E in a problem, make sure you're using natural logs to kind of deal with that if you're trying to get rid of your base. But like realistically, there's not anything new conceptually here. If you've been doing okay with what we've seen with logs so far.